Hello, my name is Matt McCaskey. I am the lead software engineer for the Regenerative Fuel Cell project at NASA Glenn Research Center, and I'm here to talk about the benefits of using electronic data sheets with coreFlight systems using the RFC project itself as an example. So for the outline of my talk, I'll start off giving a brief overview of the coreFlight systems with EDS support framework. Starting with the tool that's used to parse the EDS files themselves, which is this EDS Lib tool and the resulting database that comes from that. And then also I'll talk about the tools that are used to interface EDS specifically with coreFlight. This is the CFE Mission Lib database that gets generated. After that, I'll give a brief overview of the Regenerative Fuel Cell project itself and the software approach that we're using to satisfy the regenerative fuel cell. So we've got three programs that we're developing. The operational program and hardware simulator, both of which are using this coreFlight systems with EDS support, and the operator interface, which are using the Python bindings for these library tools that I listed above. After that, I'll go over a generic ground station software that we develop in conjunction with the operator interface that has a basic telemetry and telecommand system, but the idea behind this software is that it can interface with pretty much any coreFlight instance with EDS support. And so I will be demonstrating how that works. So the spacecraft onboard interface services, EDS XML specifications, are defined by the Blue Book, which is found at this first reference right here. These specifications are there for defining constants, data structures, interfaces, constraints across multiple packages and files. And just for clarity's sake, I will be using EDS file and XML file interchangeably because in this case, they're essentially referring to the same thing. So the tool that's used in conjunction with these EDS files is given at this second link here, this tool called EDS Lib. This contains a implementation of a tool and runtime library for embedded software to create and interpret data structures defined using these XML specifications. So when this tool is run, it first parses the XML files within a given project into a document object model tree. So we have an example, one of such trees here on the right. So generally it's a good idea to have a data sheet that contains type information that covers all of your signed, unsigned integers, floating point values, things like that. And those entries can then be referenced by all of your other data sheets. So like this data sheet has an enumeration, a container with some entries, and some various constraints. So once all of these EDS files are read into a DOM tree, this tool creates header files that contain the data structures defined in these EDS files. And it also creates a C database that contains the metadata of this tree. So base names, types, structures, number of sub-elements, sub-element information, labels, constraints, etc. And also, it also contains information for packing and unpacking data structures to and from native file structures, so whatever computer architecture you're working with. Now, the runtime library associated with this tool also contains API functions for retrieving this EDS metadata and doing this conversion between packed and native data structures. On top of that, there are bindings for scripting languages like Python, Lua, and JSON that allow the manipulation of these EDS objects within scripts. Now, in principle, this tool is application agnostic, so you can use it in a non-coreFlight scenario, but the intended use is to use this in conjunction with the following tools to work with coreFlight. And so the additional tools that were developed here for specifically interfacing EDS Lib with coreFlight. So using the interface specifications in the Blue Book, those are used to define the telemetry and telecommand interfaces of the coreFlight software bus. So things like topic IDs are constants, and you can manage those in a individual EDS file. We can use constraints to manage command codes. When this tool is run, dispatch tables are generated for applications that receive messages from the software bus. So that will associate a particular command message with the right function for processing. And then along with the C database from EDS Lib, another C database is created containing the metadata of the interface database, and that's this CFE mission lib. So this contains things like interface IDs, topic IDs, dispatch table pointers, and then associated EDS objects for all the software bus messages. So there's a runtime library associated with this to primarily get and set information in these various messages. And so this provides the conversion between things like message ID, topic ID, app ID, and this can be customized with any desired header. They just have to be defined in the EDS files themselves, and then the conversions also need to be included into the runtime library. So on top of these tools, there are additional tools that were developed to read Lewis scripts and generate binary configuration files that can be read into coreFlight at runtime. And as a technical demonstration, Joe Hickey has a repository here that takes all of these tools and combines them into one repository. And so this is the CFE EDS framework that our software is based off of. Now, the regenerative fuel cell, to go over this project a little bit, a regenerative fuel cell is an energy storage system that utilizes hydrogen and oxygen gases to store energy. So the fuel cell converts the gas to electricity and water, and the electrolyzer takes energy and converts water back to the gaseous reactants. So this diagram on the right is showing the fluid, thermal, and electrical interfaces between all of the subsystems. So the primary goal is to demonstrate an RFC system within a TVAC chamber for several lunar day-night cycles. Now, assuming a worst-case scenario at the lunar equator, the day and night last about 2 weeks. So if we wanted to bring a appropriately powered battery system, they become prohibitively expensive, which is why the RFC can come into play, because the energy storage is simply in the gaseous reactants. So if you want to provide more energy, you just provide more gas. And that's what makes them more feasible in this sort of scenario. So the RFC software itself is responsible for handling the monitoring and control of the entire RFC system. So it's responsible for managing the state machine as it transitions from the various operational modes, going from either safe, where essentially nothing is happening in the RFC system, to either your normal fuel cell and normal electrolyzer, where the fuel cell and electrolyzer are running respectively. Now, during these transitions, the software is responsible for turning on the actuators and effectors during both transitions and fault actions. All the while is constantly monitoring sensor data to make sure that they're within operational limits. So we have set up a caution, warning, and alarm system to quantify the severity of the fault. And depending on the severity, the software is supposed to automatically perform predefined actions. So these can range from just sending an alert to an operator to all the way to rapidly transitioning the system to safe by essentially turning all of the actuators off. Software is also responsible for calculating parameters related to the overall health of the RFC system, and it's also supposed to store operational data in internal files and send telemetry to a remote operator interface. So to take care of all these requirements, we're developing 3 programs. So the operational program, this is essentially the heart of the software suite. This is going to reside on the RFC system avionics. In our case, we're using a CubeSat space processor. So this manages the state machine, fault monitoring, fault actions, telemetry, and data storage. So it does a lot. It's a workhorse. The hardware simulator, this is supposed to be a development tool used to help simulate sensor values based on the current state of the actuators. And so this is used to test to make sure that the operational program is running properly. And so the hardware simulator allows us to test the operational program in multiple scenarios, whether processor in the loop or hardware in the loop. And so the diagrams of those are given here, where processor in the loop, both programs are running on the CSP board, and they talk to each other through a shared memory block to read and write actuator and sensor values. And then the hardware in the loop, instead of using a shared memory block, the actuator and sensor signals are converted to actual voltages through various analog to digital converters and digital to analog converters, so that you have a more realistic hardware scenario. And in this case, it's very easy to swap out simulated values with actual hardware, and the operational program is then none the wiser. And then finally, we have an operator interface. This is a Python-based GUI that receives telemetry from the operational program, sends commands to the operational program, and displays telemetry information in useful formats. And this also allows you to download the operational data from the operational program and for further processing on like a desktop computer. Now, I know I've already kind of spilled the beans, but both the operational program and hardware simulator are going to be based in this coreFlight with electronic datasheet support. So there are many reasons why we went with this framework. I mean, first, the generic reason that coreFlight has a history of being successfully used in flight projects. Well, the RFC project may eventually transition to a flight project, so we felt it was prudent to start with a framework that's been used in flight. But even before the RFC project, there have been several projects at Glenn Research Center that have similar requirements and that also have used this coreFlight systems with EDS support. So that gave us a very good starting point for our code base. So like the applications that we're using for like input-output data management, the state machine, fault management, all those things, the skeletons of those applications already existed before we even started. So that certainly helped us out a lot. Specifically related to EDS, the EDS files become a single source of truth for the entire project. If there's something that we need to reference, we just look at the EDS files. And then if we change anything in the EDS files, then that change reverberates throughout the entire project. So it certainly makes life a lot easier when making updates to the software. The EDS Lib API functions simplify data communication between the different computer architectures. So in our case, our laptop computers running the operator interface and the CSP board. They both have different architectures, but they both use the same API function calls to convert between the packed data structures and native data structures. So that just makes communication very easy. And then we use those Python bindings quite a lot to use the EDS objects within scripts. I mean, this is a core aspect of the operator interface. It's useful for these human readable scripts that we use to generate configuration files, and I'll be describing both of these a little bit later. And this also allows us to create functional testing environments that will speed up testing, allows us to automate things a lot easier. But then really at the end of the day, I mean, it's still coreFlight, so there's still a community of developers that we can lean to ask for help, which I've certainly took advantage of myself last year, trying to compile and run my coreFlight programs on the CSP board. So thanks for everybody who helped me out with that. Showing a quick example of one of these configuration files. We've got several configuration files that we use for the RFC project, but here's one specifically for the fault table. Now, in terms of a Lewis script, it's relatively simple. We just create an object, in this case, our fault table, and our fault table is essentially a two-dimensional array indexed by operational mode and then channel. And so for each entry in our two-dimensional array, we feed in a structure that contains the alarm, warning, and caution low and high limits. Once that table is entirely full, we then call this API function, and this creates a packed configuration file with the correct file services and table services headers that we can then load into coreFlight at runtime. And the nice thing about these configuration files is we can keep multiple copies of them for different scenarios. So, for example, in the input-output app, we can have a configuration file for like a processor in a loop, hardware in loop, and then the entire RFC system. So depending on which scenario we're going to be working with, we just load in the right Lewis script, and that will give us the right configuration file. Now for the Python bindings, like I said, these we use to create and use EDS objects within Python. Now this is where the RFC project has actually helped in development, because we've created some of these bindings out of necessity for this operator interface. So we have iterators for containers and enumerations to extract entry labels. We've got iterators that loop over all of the instances. In our case, the hardware sim and the operational program. We iterate over the topics for telemetry and telecommand and subcommands if necessary. And then also the biggest thing was we have methods that used to extract and set information on software bus messages. And so that was key to allow our operator interface to be able to handle telemetry and telecommand. So we used all of these Python bindings in our operator interface so that we can then send commands, receive and decode telemetry automatically, and then take that information and display it in useful formats. So right now I'm showing a couple of graphs that we have. So these are some pressure transducer values for hydrogen. And so as new telemetry comes in, they'll get added to the little ticker tape for this little plot. Now, in the process of developing the operator interface, we actually were able to create a generic Python-based GUI, which we call the CFS EDS ground station. And this software can interface with any instance of coreFlight with EDS support. And this tool became very, very handy. It was very useful for quick command and telemetry checking. So the system itself is pretty simple. It has a very basic telemetry system that listens for telemetry messages. Any message that comes in, it uses the EDS Lib API to automatically decode and display in the log. The telecommand system, we have several drop-down menus. And the drop-down menus allow you to specify what instance you're going to send the command, what topic, what subcommand, and any payload information that comes up. And all of this is read from the EDS files, the EDS database. And so when this ground station software is incorporated into the build process of coreFlight, the only thing that coreFlight needs to do is add the mission name, which you can see here for RFC. We'll see later in the demo for the sample mission. That's all it needs to find the right Python modules and databases to load in. And so last year we went through the release process, and so this ground station software can be found right here. So with that in mind, let's do a quick little demonstration. So I already have the coreFlight software downloaded. I've got everything set up. The ground station software downloaded. I've got my bash RC pointing to the right spot for the Python paths and library paths. Essentially followed all the instructions that are in the various readmes. But with this, we can see the ground station software is in this tools folder. So we can start off by doing a make prep step. So we can prepare. And in order to build all of the Python modules as well as the ground station software itself, we do have to do a little bit of work. There's a couple of CMake variables that we need to change. So let me... Okay. There we go. So the standalone tool for CFE Mission Lib needs to be turned on. That's fine. Configure CFS EDS ground station, that needs to be turned on. And then finally, that standalone module for EDS Lib, that also needs to be turned on. So with those CMake variables taken care of, we can build the entire project. So not only does this build coreFlight, but this runs the EDS Lib tool. It creates all of the header files that I mentioned earlier, the databases, the CFE Mission Lib database, and then it also configures the ground station software and creates the Python modules for both EDS Lib and CFE Mission Lib so that we can load them into Python and use those Python bindings. So now that that's all done, we can go into the build directory and run coreFlight. So run coreFlight just like normal. And now let's get the ground station software up. Desktop demo build XC host. Okay, so there's the mission name, sample mission, which is a good start. Let's open up the telemetry and telecommand system, and we'll start the telemetry system right away. And right now it's not doing anything because there is currently no telemetry being sent by coreFlight, but we can change that by sending the command. So we can use these drop-down menus to select the instance, topic, so telemetry lab command, and then the subcommand, enable output. A payload showed up because we need a payload for that particular command. So let's type in the home IP address. and send it. So you can see the command was sent, and we can even though we already see the telemetry system working, we can see that that command made it to coreFlight, and we can see telemetry coming in. And so the nice thing about the telemetry, you can see multiple things as they scroll past. You can see the packed telemetry message first, and then after it's been decoded, every single entry in that structure is given plus its value. And the nice thing about this is if one of these values is an enumeration, it'll actually use the enumeration label as opposed to the value. So that's why you're seeing like TLM and CFE time. You know, it's printing out the enumeration label as opposed to like a 0 or a 1 with the enumeration. So the telemetry messages that come in get sorted by topic, and so you can select one and save that specific topic if you wish. But I'll just save everything. So let's stop listening, so we can pause all the telemetry that's coming in. We can even close coreFlight. Probably don't need it anymore. Uh, but if I save all the telemetry and close out of everything, and we look in the output folder, we now have a whole bunch of binary files that can contain all of the raw packed telemetry messages that we received. So what can we do with this? Well, there's also in this folder, there's also a utilities folder. And in the utilities folder, there are a couple of more Python scripts. Basically, the command utility and telemetry decode, these essentially do the exact same thing that the telemetry and telecommand system do, but they just do it in the terminal window as opposed to a GUI. So we don't really need those. But convert TLM file, what that'll do is that'll read one of these binary files, unpack every single message that's in them, and then convert it to a CSV file. So let's run that real quick. So if I can type, Python 3 utils convert file, and let's go with the telemetry output one. So now it took this telemetry output lab binary file and created a CSV file, and that is something that you can open up in your favorite Excel type program. So if we navigate to the folder, exe host, there, output, telemetry output CSV file. We'll get LibreOffice opened up, and you can see, here you go. Every single column is one of the entries in that structure with all of the appropriate labels, and then every single value that you get. So for things like RFC operational data, this is pretty handy because you can receive a whole bunch of telemetry, put it in an Excel program, and plot it. So pretty useful tool, kind of neat. And the nice thing about it, like I said, this is generic. It can, it works with the RFC software just as well as it does the generic software from the CFE EDS framework repository. So with that in mind, that's about it. So if you're interested, be sure to check out the software. Let us know if you have any questions or comments, and thanks.